Okay, so we now move on to the next unit, which is going to be about synchronization. So we'll be looking at what is synchronization, there are some common problems which we face with regard to synchronization, some hardware and software based solutions to these problems. So before I get into all of that, I would like to start by introducing a notion called race condition. So we'll first look at this example and then I'll tell you what race condition is. So assume you have a register 1, and you have something called register 2. You have a variable count which has some value. So there are two processes which are implementing separately. So in one of the processes, register 1 is taking the value of count, incrementing it by 1 and writing it back into count. In the other process, register 2 is taking the value of count, decrementing it by 1 and writing it back into count. So this process is trying to increase this variable by 1. This process is trying to decrease it by 1. Now assume these two processes are being executed parallelly. So we saw about multiprocessors. We saw how if you have two CPUs, each of them can execute one process at the same time parallelly, right? So assume that is what is happening. One processor is executing this and the other is executing this. So there are a total of 6 instructions in all, right? So there are different ways or different sequences in which they can be executed. So assume that this is one possible sequence in which is getting executed. So let's say one of the you ignore the producer consumer words for now, we will be coming to that soon. So let's say register 1 is taking the value of count. Let's say count was 5. So register 1 now takes the value of 5, increments it by 1, the value is 6. Now before it can write, register 2 is taking the value of count, which is also 5. Remember, no change has been made to count. So it takes this 5, decrements it to 4. Then register 1 writes a 6, then register 2 writes a 4. Now if you see, ideally if these processes had been executed one after the other, if your count was initially a 5, then the increment would have resulted in a 6 and the decrement would have then resulted back in a 5. Or if they had happened in the reverse order, again it was initially a 5, the decrement would have made a 4, then the increment would have made a 5. So if your original count value was 5, and if these processes either 1 followed by 2 or 2 followed by 1, if they had been executed serially, sequentially, your ultimate value must have been 5 only in either case. But because they are both running parallelly and because there is some interference or overlap between the two, like half of the first process, half of the second, half of the first, half of the second, and so on and so forth, you are ultimately ending up with a nonsensical value, count equals 4. So what we see here is that when two or more processes are accessing the same piece of data, and when they are all making modifications to it, there is a possibility of you ending up with an incorrect or inconsistent value. See, if everyone is only going to read, then there is no problem. But when more than one process is going to write onto the same data element or the same variable or the same memory location, it is best preferred that you execute the processes serially or sequentially, one after the other, in which case there will be no inconsistency. But that is going to take up a lot of time, right? When you have multiple processes and you still expect the processes to be dealt with one after the other, you're wasting your resources, you're wasting your time. So you want to multitask, but you also want to make sure your multitasking does not make you end up with incorrect or inconsistent results. So this kind of situation where several processes access and manipulate the same data concurrently and the outcome of execution depends on the sequence is called a race condition. So a race condition is basically where you have multiple processes accessing and modifying being the keyword, the same data element. So if they are executed in different sequences, then your answer is going to be different. See, notice that in your serial execution, whether you did 1 followed by 2 or 2 followed by 1, your final answer was going to be 5 only. But here, if you execute things in this sequence, your final answer is 4. If you simply interchange the last 2 instructions alone, then your final answer will be 6. So simply because of this concurrent execution, interwoven execution of 2 processes, the sequence in which the instructions get executed seems to be affecting the output. Because both the processes are modifying the same data. So such a condition is called a race condition, and it is a problem. We need to make sure that even though our processes are being executed parallelly, the final answer we get is the right one that should be happening, and it is not affected by the sequence or the order or by interruptions. So that is what we are going to look at mainly in this chapter.